Politecnico di Torino, we successfully manufactured and scaled up a high-performing and stable electrode for converting carbon dioxide into syngas, which is a mixture of CO and hydrogen. Such electrodes are made with low-cost catalysts based on copper oxide, tin oxide nanoparticles with a very small amount of a rhenium-based complex. We deposit it with a scalable process into carbon paper to make electrodes of a size up to 100 square centimeters. And with the SunCoChem developed catalyst, we have demonstrated a steady-state production of syngas for several hours, achieving a tunable CO2 hydrogen ratio ranging from 3 to 9. The syngas can then be used as a non-fossil fuel feedstock for producing chemicals and fuels, starting only from CO2, water, and sunlight. And in the path for the development of this technology, we optimized the process conditions, including the use of different electrolytes based in water or salts or ionic liquids. We are also working in the modeling activities that support the experimental development of the project and will support the demonstration at Tier 5 of our prototype of the SunCoChem project. Since the flue gases that are produced by industrial processes contains not only carbon dioxide but also other gases like nitrogen, oxygen, and some contaminants that could hinder the CO2 conversion process, in SunCoChem we also developed and demonstrated an integrated system for the capturing of the CO2, its purification, and its subsequent conversion in the same reactor. We scaled up this technology from 10 to 100 square centimeters, which is the size of the modules of the final SunCoChem prototype. By the co-electrolysis of the purified CO2, we were able to produce syngas with a CO to hydrogen ratio of about 1:1 at -2 ampere of current and a conversion efficiency of 30%. That is relevant for the practical application of the technology at industrial level. So the produced syngas had the needed composition for being used as a feedstock for the hydroformylation process that we will use to transform waste olefin into fragrances during the Tier 5 demonstration of the project prototype. Based on the current results that we have obtained, we expect to achieve an efficiency of conversion of the sunlight to syngas higher than 10%. This is possible because, other than photocatalysts, our technology exploits photovoltaic panels that will further convert sunlight into energy that is used to drive the CO2 conversion process. Therefore, we are performing experiments for optimizing the integration of the perovskite photovoltaic cells with our tandem photoelectrocatalytic reactor to make a self-sustained system that will not need external energy sources. The modeling activities combined with experimental work is helpful for making faster progresses in the optimization of the reactor efficiency. We use multiphysics modeling tools to investigate the electrochemical processes at the micro and the macro scales. The models simulate the real reaction kinetics and mass transport phenomena in such a way that we can investigate how the CO2 reduction reaction process takes place under different operative conditions, to select the best ones for enhancing the conversion efficiency and the selectivity towards the desired product. The state-of-health diagnosis tool exploits electrochemical impedance spectroscopy measurements as a non-invasive tool to monitor how are working the different components of the electrochemical reactor, so that, in case of loss of performance, we can understand in what component of the reactor there is a problem and develop strategies to recover the activity and maintain the stability over time.